welcome to the Parametric Statistic online course. We're gonna finish today the last subject of the semester, and that's time series. And we're gonna go directly to autocorrelation where we left off last time. So you remember last time we first learned how to differentiate a time series and to decompose it, to take out the trend and the seasonality, and we're left with some random or error term which we can use for prediction. But to really understand prediction in time series, we have to learn about one last complicated thing, and that's autocorrelation. And in this course, we learn about correlation, the normal correlation, how two variables relate to each other. But autocorrelation means the same variable with itself. How do they correlate with each other? And what I told you last time is that you have a time series and you make a copy of the time series. And when you have the two copies of the time series, well, they will have a correlation of one with the other, each point with each data point at each point of time. But then you shift one of the copies one time step. This is called one lag, and we find the correlation. So every point from the original will be correlated with the point at that time plus 1. And then I will find a correlation. If I have a normal time series which have a very cyclic pattern or very like a trend that is being followed, you will see this autocorrelation is going to continue for several lags. If there's no information after some time steps, then the autocorrelation will disappear after some lags. And this can be seen better in an ACF plot. And this is not an easy plot. You have to believe me that this is one complete semester of time series. Normally, econometrics, economic students take one complete course on time series, and they just learn to understand this plot, the ACF plot, which is there's the lags, lag 0, lag 2, lag 3, lag 4, 4 and 5, and you see how much after each lag, how much autocorrelation there is. For example, in this first case, we have in the 0 lag, it has a correlation of 1. This is normal, that it has a correlation with itself. But then you see in the lag 1, there's a very small correlation, autocorrelation. So this means that at time plus 1, there is few information about the time series, okay? So probably this doesn't look more like a time series anymore. And these two lines are the confidence intervals. If the bars are inside of these intervals, it means that it's not significant, the autocorrelation. There's a 5% of non-significance that we have been finding in the normal correlation, the Pearson correlation statistics, if they're significant or not. If we look at this second plot, we look that there is autocorrelation in the first one. There's still a big, almost 0.5 autocorrelation. Then it's smaller. Yeah. What this means is that at the lag 1, there is still information about the previous time. Okay, so this like they are related until approximate time 3. It is also possible that it's not only positively autocorrelated, but also negatively autocorrelated, like here. In here we have positive with itself, and then a negative autocorrelation, and then positive, negative, positive, negative. And what kind of exactly time series would give this? So for now, it's not important that you think about how it was generated, but it's more to try to interpret it. Okay? It's like if you have, in this plot you see you have each point, it's a data point at a given time, at lag 0 and lag 1, and we can see if they are correlating or not. So in this plot you see no correlation. In this plot you see some positive correlation between the two lags, and here you see some negative correlation. And we're going to use this plot to be able to see to use our models for predicting in time series. But let's go directly to when are we going to use this HfP plot, because it's already complicated enough, but then it will make a little bit more sense when we find out why are we learning this. Well, we're learning it because we want to learn to forecast. Forecasting is what happens in the weather when they want to predict what is going to be the weather tomorrow or in 1 hour. That's called forecasting. And weather is exactly a time series. Yeah. Until now, we have used linear regression to predict new values. But with time series models, we need to predict not values like in the linear regression, but future values, because we are in time. And this is called forecasting. And there are 3 types of technique. The first one, you find a lead variable that is related with the variable to predict. For example, weather. If you find that the temperature will depend on how much sun there will be, so the lead variable could be sun. If there's going to be a lot of sun, probably the weather is going to get warmer. Yeah, so it's something that influences the time series where we are. A second technique is to find something similar data, for example, from other products if you're trying to predict sales, and use this knowledge to predict the variable. In the case of the weather, it would be like taking the temperatures from the year before and how did it evolve through time in the last 50 years. So that could probably be like similar data. And the third technique is called extrapolation. It means we use the same time series, we don't use another variable, and we try with just this data, very similar to linear regression, we try to predict, make a forecast. And you should use this one only when you're sure that the trend will continue with the time. Because if it's gonna change, like stock market, that you know that it can change at any minute, then the extrapolating would be a bad idea. And there are many models to predict time series. We could have a whole semester. But for now, I'm gonna show you the most famous one, and it's like the basic of forecasting. It's called ARIMA. Yeah, and it's extrapolation technique. It's one of these techniques. ARIMA, and that's one of the most famous. As ANOVA was the most famous for linear regression, ARIMA is the most famous for forecasting in time series. Okay, so let's try to see how it works. And it's gonna be a surprise because it's gonna be like a linear regression. Yeah. So ARIMA is a multiple linear regression model, but takes into consideration autocorrelation. So autocorrelation is very important, and that's what it tells us to create the linear model. And the assumption is the time series is stationary. So first you have to make sure that it's stationary. That means it should not have a trend nor seasonality. So you have to either decompose it, or if you're not sure what is the trend or the seasonality, you can simply differentiate the series, like take continuous values and subtract them from each other. Okay? And the idea is we want to include autocorrelation. How do we do it? Well, we're going to use the lags and the errors as predictor variables. And before we go on, these errors are not the remaining part of the time series. Let's call that random, okay? Because if you think here are the original errors from like linear regression, there are errors, they're real errors, okay? Don't get confused. And here's how we're gonna predict. We're gonna predict the variable at the time, at a given time, will depend on the previous times. It will depend on the value at one time before, and it will depend on the value 2 times before, and 3 times before, and 5 times before, until p times before. You have to decide how many times before, and each of these values will have a coefficient. Beta 1, beta 2 to beta p. Yeah? It's the same coefficients as with multiple linear regression, but we're not taking other variables to predict, but itself. And this is why autocorrelation is important, because autocorrelation tells us how much information of the time series can be found in the past, because we're using like the past to predict the future. We're using the previous time steps to predict the new time step. And if we don't have autocorrelation at all in lag 1, then this prediction will be a very bad prediction. Imagine this is y and this is x. And if there's no correlation, imagine there's only this. Forget about the rest. There's only this. And it's a normal linear regression. If there's no correlation between y and x, then the linear regression will be bad, right? We need a high correlation so that there's a good model. Remember? When we only have one predicting variable. And that's why when we have autocorrelation, we can use this previous time step because they are correlated with the future time step and they bring some information with it. So autocorrelation is good. And we want to make first the series stationary because when we take out the trend and we take the seasonality, there will be very few time steps in the past which are very relevant, and then the other ones will not be relevant, okay? Because if we didn't take this out, we will need like almost all the previous time steps because there will be some correlation between this one and this one. So the better to do a stationary to need few number of observations of predictors from the past. Okay? And this part of the equation is equal to the AR of Arima. Okay? There's a second part of the equation. There's this second part of the equation. And it all again looks like a linear regression, but like another model. So imagine it's a second linear regression, we're just summing it, and then we're going to use other letters, we're going to use alpha instead of betas, but they are the same, they are coefficients. Don't get worried, they are coefficients. In this case, we have the errors. We have error at time t, error at time -1, error at time -2, until time minus q, so some times of error. But what is error? So I haven't explained it actually. Error, which I call here E, but it's actually error. This is error, where error is the difference between the moving average at a given point in time and the actual value. So if you remember, when we were using moving averages to find the trend, we would take values, consecutive values of the time series and average them and get an average value. And the difference between the real value and the average value between the points in the neighborhood, that would be like an error. And this is the error at that time point, the error at the time before, and the error before that, and so on and so forth. Yeah? So remember, moving averages takes the mean of consecutive values. And at the end you get this model, which is a really long multiple linear regression, which depends on previous time steps and errors between the real values, this value as xt minus 1, and the moving average value, which is the average between the consecutive points. And this is one very, let's call advanced model for time series. It's really a good one, like a good model. And it really is a good model for predicting future points. Okay, so how do we find the number p and how do we find the number q? That would be like the question, right? How many time steps do we go into the past? And here is where we want to call p the number of autoregressive terms and q the number of moving average terms. Autoregressive is the AR, moving average is the MA. And the I is missing. Where is the I? So P is the number of lags that we include in the model. So lags means previous time steps. And Q is the number of error lags that we include in the model. For example, if P is 5, then we'll use the predictors from times -1, -2, -3, -4, -5. And if Q is 5, it can be different. Q and P do not have to be the same. Then the predictors for xt will be error t until error t minus 5. Okay? So how do we decide for the best values of P and Q? That's the question. That's the last thing we have to learn. Because if you see, this is simply a multiple linear regression. So you can calculate it the same way that you learn to do linear regression. It's finding the coefficients that find the lowest error, that reduces the RSS, the residual sum of squares. It's the same thing that we learned before, just with different predictors. The same points in the past, and the errors will be our predictors. But how many do we include? This is where the HfP plot comes into consideration. Okay, we're gonna use the HfP plot to find the best Q, the error lags. Okay, and the technique or the recommendation is to choose Q as the lag which crosses the upper confidence interval for the first time. So this is the upper confidence interval. And if we see here, this one does not cross it, this one doesn't cross it, this one doesn't cross it, this one crosses it. Okay, so it means we're gonna use the Q3 because these are the ones, these three, the 1, 2, and also 3 are the ones that are telling us the most information about the time series. Okay, and then how do we find P? Well, to find P, we're gonna need another similar plot, which is called the P-HcF plot, and the P does not come from this P, but from partial HcF. And it's the same thing as HcF, so it also measures the correlation, the autocorrelation between the time series and the versions of itself, but it eliminates the variations already explained by the previous lags. So if we have lag 0 and lag 1, we have the autocorrelation, and then when we go to lag 2, we'll have autocorrelation with the lag 0, but there will be some part of lag 1 that was already explaining this autocorrelation, and we take it out. That's why it's called like a partial. And we choose P as the lag which crosses the upper confidence interval of the P-HcF for the first time. So an example, we have the HcF and the P-HcF of a time series. With the HcF we can find the best Q, and in this case is here 9 is for the first time it crosses this confidence interval, so Q is 9. And in this case the partial, it's in a lag, this is 0, 1, 0, 1, 2 is the one which crosses the first one for the first time. Three, 4, 5. Yeah, this is 3, exactly. 3, 4, 5, 3. So now that we selected P and Q, and what we're gonna see tomorrow in the tutorial, there will be a way that you don't need to actually choose them, so don't worry. The program will choose them for you to find the best one. So these are just like yeah, like it's good to do it like to choose P and Q like this, but there could be other ways that the model is better. So it's not like it's a recipe, but it can go wrong. Okay, this is how they suggest you to do it. Okay, but now that you selected P and Q, we can fit the model the same way we fit multiple linear regression. So you will have the blue one is the original line, the red one is the fitted one, and it doesn't look as perfect, but it's not we don't want to overfit. Remember, it's again we don't want to overfit to create the same line, because there are some errors and we don't want to predict these errors. Okay, and remember this time series has the trend and seasonality taken away, so we need to add it back if we want the original time series and our fitted model. So we have to add it again, and at the end you will have something like the original time series, and you can make forecast. How do we forecast, which would be like the last step? Well, we use the model we created. We have a linear model, and we need to start extrapolating. And this is how you do it. You obtain the last value in the last time point, and you use this one to predict the next data point. And after that point, you predict the next data point and the next data point, and you go one time step at a time. And it would look like this. Like you have this time series that is increasing, and then until here is your data, and from here on, this part is the forecast. It goes similar up, up, and down. And the purple things are the confidence intervals. How confident is your model that it will be there? The 95% confidence interval. An important thing to know is that ARIMA is only good to make short-term predictions. So for some time steps in the future, yeah, it's gonna help us, but for a long time, it will not help us at all. Okay? This is just to look a small part into the future. We cannot look complete into the future. Okay? And I know there are a lot. There may be some questions because time series is not an easy topic, and we're gonna any questions you have, you can tell me tomorrow on the tutorial. Okay, we'll explore all the questions. If I said something wrong, I'm sorry. It may happen. I don't know, but we can look for it tomorrow at the tutorial. And that's it for my side.